All right, so this is the first lesson looking into the idea of antiderivatives and leading us toward the idea of integration or integral calculus. And an antiderivative is a fairly straightforward idea. As it sounds, it's the opposite of the derivative, or going kind of the other way. And as for some notation here, going forwards, anytime we have an uppercase letter, that denotes the antiderivative of the lowercase. So uppercase f of x represents the antiderivative of f of x. Or as it states here, if uppercase f of x is some function, its derivative is lowercase f of x. Just sort of a simple common notation to use to denote uppercase and lowercase. Use uppercase and lowercase letters to denote a function and its antiderivative. All right, so first if I want to look at a number of examples here. And again, I just first start with essentially what I just said. If we have some function, some constant times a function f of x, the antiderivative is denoted with an uppercase letter. And if we have a couple different functions being added to each other, f and g, their antiderivatives are uppercase letters, uppercase f, uppercase g. So a bit more specifically, let's look at essentially some of our differentiation rules in reverse. And so if I look at this one, this is the power rule in reverse. If I have any power function, x to the power of n, as long as n does not equal -1, what you see off to the right is the power rule in reverse. So the antiderivative of x to the power of n is x to the power of n plus 1. We add 1 to the power. And then we divide also by n plus 1. And this denominator here may seem a little unusual too, as well as this c, which represents some constant. Let me just explain those quickly so I can move on to other ones. So for example, if I just have x to the power of 4, using the power rule backwards, what I just had up there, the antiderivative of this would be x to the power of 5 divided by 5. That's the antiderivative. And if you're not sure if that's correct, just look at it the other way. Let's differentiate this, just using the power rule. So if we differentiate this, we get 5 times x to the power of 4 divided by 5. The 5 cancels out, and you can see we're correct. And I can do this with any number, any power function. As for that constant, remember if you are differentiating any function, because again, if we're differentiating, we're looking this way. If we're anti-differentiating, we're looking this way. But if you're differentiating any constant, the derivative of any constant is 0. And so anytime we're anti-differentiating, we can't forget that there may be some constant there. And that constant can be any constant number, because when you differentiate it, it'll become 0. And we never have to really think about that when differentiating. But when you're anti-differentiating, we always want to remember there can always be a constant. And again, if you look going this way, whatever number I have there, if it's a constant, the derivative of that will become 0, which means it's going to be equivalent. So there's always a countless number of different but similar antiderivatives for any single function. And they're differing by, they can have any sort of constant. Okay, another example. What if you actually have x to the -1? Like I said, the power rule here, what I had here is correct as long as x did not equal -1, or sorry, n did not equal -1, the exponent. Well, if you have an exponent of -1, it means this. X to the -1 means 1 divided by x. And in this case, if you try to use that power rule backwards, you get x to the power of 0 divided by 0, which doesn't make sense because you're dividing by 0. However, hopefully we can remember that 1 over x is the derivative of ln x. And so the antiderivative of 1 over x, or the antiderivative of x to the -1, is the ln of x plus some constant. Now, notice I have absolute value right here because, well, let me show you an example. And I have a little star leading to these two examples right here. So notice, let's look this way. Let's look at differentiating, which we're familiar with. The derivative of ln x is 1 over x, right? But let's look at what's the derivative of ln of -x. Well, in this case, we have to use the chain rule. So first we find the derivative of ln of the outside function, so it's 1 over -x in this case, times the derivative of the inside function, which the derivative of -x is -1. And this simplifies down to 1 over x. So notice it doesn't matter if we're looking at the ln of x or the ln of -x. The derivative of both is the same. And so when we're anti-differentiating, we're looking backwards. So it doesn't matter if we are, it doesn't matter essentially which one we look at. They're both correct. And so I kind of essentially summarize that as what you see right here. So the ln of the absolute value of x kind of takes that into account, essentially saying it doesn't matter what whether your input is -x or x. The derivative will be the same. And so therefore the antiderivative, those absolute values kind of cover both those cases. If we ignore negatives, though, then you can ignore that absolute value there. But essentially, the derivative of 1 over x is the ln of x plus some constant. All right, e to the power of x, lovely simple function. The derivative, or the antiderivative, is e to the power of x plus some constant. B to the power of x, any other exponential function, as long as b is not Euler's constant. The antiderivative is b to the power of x divided by the ln of b plus some constant. So again, just like the derivatives of an exponential function are much more pleasant if you're dealing with e instead of another power. Same thing for antiderivatives. It's not crazy complex. You have this, you're dividing by the ln of b. But it's obviously going to be more pleasant if we have a base of e. And again, if you're unsure about any of these, just look at them this way. Just use all the many things we've learned about differentiating, and it'll kind of prove that they're correct. And again, that constant, any number, will always come to 0 when you differentiate. A few more examples I want to look at. I think fairly straightforward. The antiderivative of sine is negative cos x plus some constant. The antiderivative of cos x is sine x plus some constant. And again, easy to check in reverse. The antiderivative of secant squared is tangent plus some constant. And I mean, there's lots of examples. I just have one of the reciprocal ones here. The antiderivative of secant x tan x is just secant x plus some constant. Now again, I don't expect you to have memorized in advance the derivatives of the reciprocal trigonometric functions, but if you look back, for the derivative of secant x, the derivative of secant x is secant x times tan x. And so it makes sense, the antiderivatives like this. And then we have a couple of our inverse trigonometric functions. The antiderivative of 1 over root 1 minus x squared is arcsine, and the antiderivative of 1 over 1 plus x squared is arctan. And again, there were others. Arc cos is the same as arcsine, except there's a negative right here and so on. I just want to touch upon a number of examples, but it's all just built upon the stuff we've done, in the last several units, but looking at it backwards. And then again, easy to forget the importance of the relevance of there's always a constant here. And that constant could end up being 0, but there could be any real number. All right. So let's just do a few examples. I have a prime being this function you see here. Let's find a of x, which really I'm asking for the antiderivative of the function I gave you. And so one thing I would do right away is focus on this part here. That's probably the trickiest looking part. The derivative of 4 sine x is relatively simple. What about this 2x to the power 5 minus root x over x? Well, just like if I was differentiating this right here, I would not actually differentiate right away. I would break this up into a couple of terms using the power rule. So that's what I'm going to do as well. I want to break this up into a couple of terms using exponent laws and then eventually use the power rule backwards. And so again, I'm not going to differentiate yet. So a prime of x equals 4 times the sine of x plus, if I look at this as, think about this divided by this, I have 2x to the power 4 minus, if I think about this divided by this, I have x to the negative 1/2 if I use my exponent laws. All right, so now I'm going to anti-differentiate this, because now I can just use, essentially examples that I had from that table a moment ago. So the antiderivative, or in this case just a of x, because a prime was the derivative. The antiderivative of 4 sine x is 4 times minus cos x. Plus, the antiderivative of 2x to the power 4 is 2 times x to the power 5 divided by 5. Minus the antiderivative of x to the negative 1/2 is we add 1 to the exponent, so x to the positive 1/2 divided by 1/2. Again, always divided by 1 plus the power. And so all I want to do is clean this up now. This is needlessly messy. So I have minus 4 times the cosine of x plus 2x to the power 5 over 5. And over here, dividing by 1/2, same as multiplying by 2. So minus 2x to the power of 1/2. And then I really should say plus some constant. To be honest, I should have put it back there as well. And so just like when we're differentiating, I didn't rush to anti-differentiate. I used exponent laws, rewrote one of my expressions so that I could use the power rule backwards. All right, here's a second last example. I give you the second derivative of some function. So I say b double prime is 12x squared plus 6x minus 4. And then I give you a couple of facts about function b, not the second derivative. B at 0 is 4 and b at 1 is 1. So from that, we have enough information to determine an equation for b of x. So first, let's look at my second derivative. And just like when you're differentiating, we're dealing with polynomials, it's really quite pleasant with anti-differentiating. So b prime of x would be 12 times x to the power of 3 divided by 3, plus 6 times x to the power of 2 divided by 2, minus 4 times x. You could say to the power of 1 over 1, or really just 4 times x. And so that's it. I should have a constant right here. All right, I could now move on to my second derivative, sorry, to my main function, but let me clean this up a bit. So I'll write it as 4x cubed plus 3x squared minus 4x plus c. And remember again, if at any given point you are unsure about one of these, just go back, right? If I'm unsure, just double check, use my power rule. I'll quickly see I'm correct. It's really easy to check, especially when you're dealing with the power rule. All right, so that's my first derivative. Keep in mind I have that constant. And right now that constant can be anything. But eventually I want to know what that number is. However, let's leave it like that for now, and let's find my main function. Let's anti-differentiate again. And again, use the power rule backwards. So the antiderivative of 4x to the power of 3 is 4x to the power of 4 divided by 4. And so that's just use my power rule a few times. And then we have this constant. I don't know yet what that constant is, but if I anti-differentiate it, it's going to be plus c times x, which again, essentially I'm using the power rule backwards. You can think of it as c times x to the power of 0. Add 1 to there, divide by 1. But again, since I am anti-differentiating again, there's another constant here. So I have a c, and now I have a d, I'll call it. OK, and so let me clean this up. But I need to figure out those constants. Otherwise, I haven't figured out this function. Good thing is it simplifies quite nicely. All right, so this is where I need to take into account those two extra little facts I was given. B at 0 is 4, and B at 1 is 1. And so let's just look at my function b of x and replace x with 0, because I know that b at 0 is going to be the same as 0 to the power of 4 plus 0 to the power of 3 minus 2 times 0 squared plus c times 0 plus d. And I know that equals 4. So really quickly, I know that d must equal 4. Because everything else is 0. All right, so now I know one of my two constants, d is 4. And so similarly, let me use the other fact about when I said b at 1 equaled 1. So replace all my x's with 1. 1 to the power of 4 plus 1 to the power of 3, and so on. And I now, again, c times 1 plus 4 equals 1. So this time, all I have left, the unknown, is whatever c equals. And pretty quickly, I can just solve for c. And when I get here, I get c plus 4 equals 1, which means c equals negative 3. So there we go. Now I can put my whole function together. I can say all together, I can say b of x equals x to the power of 4 plus x to the power of 3 minus 2x squared minus 3x plus 4. There we go. Keep in mind, if I wasn't given those 2 points of information about function b, then it would be impossible for me to know what c and d are. They could literally be any constants. And this last question is kind of applying these same ideas to some sort of basic physics. Here's the last question. And so a ball is thrown upwards with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground, assuming a gravitational constant of negative 32 feet per second. And I will say that part there, that's the acceleration due to gravity. That's the equivalent of negative 9.81 meters per second squared in metric, you see a lot in physics, basic physics courses. That's the equivalent in feet instead of meters. Negative 32 feet per second squared. The question is, when will the ball hit the ground? As I said, you're throwing it from the top of this cliff. At some point, how long will it take? When, so in time, will it take to hit the ground? Well, the first thing we need to realize is this gravitational constant of negative 32. That is the pull of gravity. And the pull of gravity is the acceleration. When you throw something up, if there is no gravity, it just keeps going up forever. But the reason it doesn't is because gravity is pulling it down. And so that negative 32 is our acceleration function. So the a of t, or the second derivative of displacement, is negative 32. Sorry, I wrote negative 32t for a second. Just negative 32. Again, it's a constant, which makes sense. It's gravity. Doesn't matter what time it is, it's pulling the same rate. So there's my acceleration function. Well, okay, that's our starting point. And if this is in metric, it would be negative 9.81-ish. So let's now find the antiderivative of that. And I could say capital A of t, or just velocity. And so the antiderivative of this will be negative 32 times t plus some constant. Okay, but I do know something about the velocity from the question. It says there's an initial velocity of 48 feet per second. So that means when time was 0, the output was 48. So I now know that v at 0 equals negative 32 times 0 plus some number, but I know that's going to equal 48. Because they tell us you threw it upwards at initial speed of 48 feet per second. Which means really quickly I can see that this constant number must be 48. Which means now I know my entire velocity function. It's negative 32t plus 48. There's my velocity function. All right. Well, perhaps not surprisingly, it's going to be useful next to find my displacement function, or my position function, which we usually relate with a letter s. So I could say capital V of t, or s of t, the antiderivative. And so again, using the power rule, I get negative 32 times t squared over 2 plus 48 times t plus some new constant. I'll call it d. And again, let me clean this up a bit. Negative 16 t squared plus 48t plus some constant. So that's my position function. But again, I need to figure out d. And again, I can do that because they tell us we throw this from the edge of a cliff 432 feet above the ground. So that means when time is 0, the displacement is 432 feet. And so I now know when s is 0, I have negative 16 times 0 squared plus 48 times 0 plus d, but I know that equals 432, and so I know that d equals 432. Now I got my displacement function. All right, so now that I have my displacement function, I can answer the question. The question is, how long does it take for it to hit the ground? Well, it hits the ground when the output of my displacement is 0. Assuming that I've set up 0 to be the bottom of the cliff, which is, I know what I set up as soon as I put this 432 right there. I'm saying that at time 0, the position was 432 meters, or feet, I guess in this case. And so I've chosen to set this up so that 0 represents the bottom of the cliff, and the 432 is the top of the cliff. And so I just need to make my position function equal to 0. And so 0 equals negative 16t squared. And now we just have a quadratic function to solve. Good thing is you can divide both sides by negative 16. If you do that, you get t squared minus 3t minus 27 equals 0. This doesn't factor, but you can use the quadratic formula. And so you get t equals, once you use the quadratic formula, 3 plus or minus 3 root 13 over 2. That's just using the quadratic formula. I've already cleaned it up. However, I know in this case, in the context of the question, negative time does not make sense in this question. That's before I threw this ball. And so it's only going to equal actually just a positive 3 plus 3 root 13 over 2. Or if you decimalize it, you get about 6.9 seconds. And so in the end, as we can see, if you were, let me zoom out a bit here, standing at the top of a very tall cliff, 432 feet, be careful, but if you threw this ball up in the air, it would hit the ground just shy of 7 seconds later, according to these models. And really, the only thing that's incorrect about these models compared to real life is that this ignores air resistance. But in terms of everything else, it's a very, very good model. And really, notice what I did was very similar to the previous question, where I started from the second derivative and worked my way backwards, figuring out constants eventually. And that's it.